Okay, here's a thought. What if I told you the universe is not just, ballooning outwards, but the rate it's expanding is actually speeding up? Think about that. It's like the ultimate unclenching, a cosmic exhale that's just getting stronger and stronger. What could possibly be like flooring the accelerator on the whole universe?
That really is the billion-year question, isn't it? And in this deep dive, we're going to try and tackle that. We'll venture into cosmology, using our notes here as a guide.
Right.
The idea is really to unpack the key concepts behind this expansion and all the weird stuff that seems to dominate the universe.
Yeah,
But keep it digestible. Hopefully spark a few aha moments for you along the way.
exactly. We want to cut through some of that cosmic fog,
Mhm.
give you a clearer view of what's, frankly, an incredibly strange and fascinating picture. So, what's the plan? What's on our cosmic road trip itinerary?
Well, we should probably start with how we even figured out the universe is expanding in the first place.
Good starting point.
Then we can dive into those big mysteries.
Yeah.
Dark energy and dark matter.
Mm.
The unseen heavy hitters.
The 95% we can't see.
Pretty much. And maybe finally touch on some of the head scratchers that still have cosmologists puzzled, ready to jump in.
Let's do it. So, the expanding universe, where did that idea even come from? It wasn't always accepted, right?
Oh, definitely not. It wasn't an overnight thing. It involved work from several pioneers, really. You had Vesto Slipher back in the early 20th century.
Slipher. He was looking at galaxy spectra.
Exactly. He noticed the light from many distant galaxies was shifted towards the red end of the spectrum, redshift, meaning they were moving away from us.
Okay.
Then a bit later, Edwin Hubble connected those redshifts Slipher found to the actual distances of the galaxies, and he found this clear relationship. The farther away a galaxy is, the faster it seems to be moving away.
Hubble's law. The farther it is, the faster it recedes.
That's the one.
Yeah.
And we should also mention Georges Lemaitre. He'd actually proposed an expanding universe before Hubble's observations, based purely on Einstein's equations.
Right. The theory came slightly before the definitive proof, in a way. So Hubble's work in 29 really sort of nailed down the expansion idea, but then the story took a twist.
A big twist. And this is where it gets really interesting. So picture astronomers back in, say, 1997. They're studying these specific kinds of exploding stars, type ES supernovae, like supernova 1997.
Ah, the standard candles. Because they should all have roughly the same peak brightness.
Exactly. Like cosmic light bulbs with a known wattage. So by comparing how bright they look to us versus how bright they should be, we can work out how far away they are.
Makes sense.
But what they found with these really distant ones was, well, they were dimmer than expected.
Dimmer, meaning farther away than they should be.
Precisely. Farther away than they would be if the universe's expansion was just coasting or, as everyone expected, slowing down due to gravity.
So it wasn't slowing down, it had actually sped up.
That's what the data pointed to. It was like throwing a ball up in the air and watching it accelerate upwards instead of slowing down. Totally counterintuitive.
Okay, so if gravity is the cosmic brake, what's hitting the gas pedal? That's where dark energy comes in, this mysterious stuff.
That's the term we use, yes, dark energy. We need something to counteract gravity on these huge cosmic scales and explain the acceleration. Its fundamental nature. Still a huge puzzle.
But we have a placeholder, right? The cosmological constant.
We do. The simplest explanation, and the one that fits the data best so far, is Einstein's cosmological constant, lambda, the Greek letter to take it. You can think of it as a constant energy density that's just inherent in empty space itself.
Energy of nothingness.
Sort of, providing this persistent, gentle outward push everywhere.
Okay, that sounds simple enough, but then you hear about this cosmic coincidence problem. What's that about? It sounds complicated.
It is pretty mind-bending. It basically comes down to the initial conditions. For the universe to look like it does today, with the amount of dark energy and matter we observe being, roughly comparable now, the ratio between them in the very, very early universe, like back near the Planck time, the earliest moments we can even theorize about,
Yeah.
that ratio had to be fine-tuned to an absolutely insane degree.
How fine-tuned?
We're talking something like 96 decimal places.
96.
96 significant digits. If that initial ratio was off by even a tiny, tiny fraction,
What would have happened?
well, either matter would have dominated way too early and the universe might have just collapsed back on itself before stars even formed, or dark energy would have taken over immediately, expanding space so fast that no galaxies, no structures could have ever formed. Everything would just be too spread out.
Wow, 96 decimal places. That's not a coincidence. That feels like something we're missing. Okay,
Yeah.
so that's the accelerating expansion, dark energy fine-tuning. But the dark side doesn't stop there. We've also got dark matter.
Indeed. the other big mystery component. And the evidence for dark matter is pretty overwhelming, actually. It comes from lots of different places, all pointing to the same thing.
Huh.
There's way more mass out there than we can account for with stars, gas, and dust.
Oh, cool. Like what? What's the evidence?
Well, one of the first big clues came from galaxies themselves, how they rotate.
Right, the spinning too fast thing.
Exactly. You'd expect stars further out from the center of a galaxy to orbit slower, right? Like planets in our solar system, Mercury zips around, Neptune crawls. That's Keplerian motion. Gravity gets weaker with distance.
Makes sense.
But when we look at galaxies, the stars out at the edges, they're moving just as fast as stars closer in. The rotation curves are flat.
They don't slow down.
Nope, it's like there's this huge invisible halo of extra mass spread throughout the galaxy, providing extra gravity that keeps those outer stars moving fast. That's dark matter.
Like an invisible anchor holding them in.
Okay, what else? Galaxy clusters. Yeah. These huge groups of hundreds or thousands of galaxies, they're filled with incredibly hot gas that emits X-rays. The temperature of that gas tells us how strong the gravity is, holding it all together. And again, the gas is way hotter than it should be based on the gravity from just the visible galaxies and gas alone. You need a lot more mass dark matter to create that deep gravitational well.
So it's holding clusters together too.
And even on the largest scales, the formation of the cosmic web, this structure of filaments and voids made of galaxies and clusters,
Yeah.
simulations show that the gravity from just ordinary matter isn't nearly enough to form those structures in the age of the universe.
Yeah.
You need the extra gravity from dark matter acting as a sort of scaffolding, clumping together early on and pulling the ordinary matter in.
So dark matter is basically the invisible architect of the universe.
Now,
But our best model for it, cold dark matter, it's not perfect, is it? There are some small-scale issues.
that's right. The cold dark matter, or CDM paradigm, works incredibly well on large scales, but when you zoom into individual galaxies and their surroundings, some discrepancies pop up.
Like what?
One is called the Coracust problem. CDM simulations predict that the density of dark matter should rise really sharply toward the very center of galaxies, forming a steep cusp.
A density spike.
Yeah. But observations, especially in smaller dwarf galaxies, often suggest the density profile is flatter near the center, more like a core.
So theory predicts a peak, but reality sometimes shows a plateau.
Kind of, yeah. Then there's the too big to fail problem. CDM simulations predict that a galaxy like our Milky Way should have more massive satellite galaxies orbiting it than we actually see. Some of the predicted satellites seem like they should be too big and dense to have avoided detection by now.
We should have found them, but we haven't.
That's the puzzle. And related to that is the missing satellites problem. Just generally, we see fewer small satellite galaxies orbiting the Milky Way and Andromeda than the CDM models predict we should.
So the theory overpredicts these galactic companions, especially the smaller ones and maybe the denser ones.
It seems to, yeah, which has led people to explore alternatives.
Like, what if dark matter isn't quite so cold? Maybe warm dark matter?
That's one idea, WDM. If the dark matter particles were moving a bit faster in the early universe, if they were warmer, that could potentially smooth out those central cusps and suppress the formation of the smallest satellite halos.
Would that fix the problems?
It might help with some things. But observations, especially looking at how light from distant quasars is absorbed by gas clouds, the Lyman alpha force put pretty tight constraints on how warm WDM could be. And for the allowed masses, it's not clear it solves all the problems better than CDM.
Any other ideas?
Well, another avenue is interacting dark matter. What if dark matter particles don't just interact via gravity? What if they could, bounce off each other?
Like billiard balls.
Sort of. Self-interactions could potentially scatter particles out of the dense central cusps, creating cores. It might also affect how satellite halos form. There's even speculation about multiple types of dark matter that could interact or mix. The dark sector could be more complex than just one particle.
It really is humbling how much we just don't know about most of the universe's contents. Okay, let's zoom out again. The overall structure. We often hear about the cosmological principle. What's the basic idea there?
Right, the cosmological principle, it's really a foundational assumption. It basically says that if you look at the universe on large enough scales, it's pretty much the same everywhere and in every direction.
Homogeneous and isotropic?
Exactly. Homogeneous means uniform distribution. Isotropic means it looks the same whichever way you look. And this isn't just a guess. We have strong evidence for it.
Like the cosmic microwave background?
That's the best evidence, yes. The CMB, the afterglow of the Big Bang, is incredibly uniform across the entire sky. Tiny, tiny temperature fluctuations, but remarkably smooth overall. Also, large galaxy surveys show that matter distribution gets pretty uniform once you average over, say, a few 100 million light years.
So if you zoom out far enough, it all looks the same.
That's the principle. And it's incredibly useful because it lets us describe the entire universe's geometry and evolution with relatively simple mathematical models, like the FLRW metric.
FLRW, Friedman, Lemaitre, Robertson, Walker.
That's the one. It's the standard model for the geometry of an expanding, homogeneous, isotropic universe. Think of space itself as this fabric that's stretching. The FLRW metric describes that stretching fabric. It includes the scale factor, AT.
Which tells us how much bigger the universe is compared to some earlier time.
Right, and it also includes a curvature parameter, K, which describes the overall shape of space. Is it flat like a sheet of paper?
Okay.
Positively curved like the surface of a sphere, K plus 1, or negatively curved like a saddle, K1.
And current observations suggest it's pretty flat.
Very close to flat, yeah. Now, within this FLRW framework, cosmologists often use something called conformal time. Why is that useful? Conformal time. What can they? It's like a tweaked way of measuring time. It's defined so that light always travels the same co-moving distance in a given interval of conformal time.
Co-moving distance. You mean distance measured on the expanding grid itself?
Exactly. It effectively factors out the expansion when you're thinking about how far light can travel. It's really helpful for understanding things like the particle horizon line, the maximum distance light could possibly have traveled since the Big Bang up to a certain time. This relates to puzzles like the horizon problem in the CMB.
Okay, so it simplifies tracking light signals across cosmic history and helps understand causal connections in the early universe.
You got it. And the engine driving all this, the expansion rate, how it changes, is described by the Friedman equations.
The master equations of cosmology.
Pretty much. They link the expansion rate, specifically the Hubble parameter, to everything in the universe, the total energy density from matter, radiation, dark energy, plus that curvature term K and the cosmological constant mode. They tell you how the universe's contents dictate its expansion history.
So the stuff in the universe tells space how to expand.
In essence, yes. Now let's talk about that stuff, the ingredients. We categorize them based on something called their equation of state.
Which is the ratio of pressure to energy density.
Yeah.
W is blah.
Exactly. And that W value is crucial because it tells us how the density of that particular component changes as the universe expands, as the scale factor AT grows.
Different stuff dilutes differently.
Precisely. Take ordinary matter baryons and cold dark matter. We call that cold matter, or sometimes just dust. Its pressure is basically zero compared to its energy density, so, hey, zero.
Okay.
As the universe expands, the volume increases like a cube. The density of matter just goes down proportionally like 1 AO. It just thins out.
Makes sense. Same amount of stuff, bigger box.
Right. But now think about radiation photons, for example. They have pressure. For radiation, W13.
Okay, so it has pressure.
Well,
how does its density change?
it drops faster. Its energy density goes down like 1 AO.
An extra factor of AKY.
Because not only is the number of photons per unit volume decreasing as space expands, like matter, but the energy of each individual photon also decreases because its wavelength gets stretched by the expansion. It gets redshifted.
So double whammy. Volume increases and each photon loses energy, so radiation diluted faster than matter.
Exactly. Which means radiation was much more dominant in the very hot, dense early universe than it is today.
Right. Now, how does dark energy fit in? The cosmological constant. What's its W?
For the cosmological constant, W1 negative pressure.
-1. What does that mean for its density?
It means its energy density doesn't change as the universe expands. It stays constant.
Wow.
It's constant.
Wait, the density stays the same even as the volume increases? How?
It's weird. It implies that as space expands, more of this energy just appears to keep the density constant. It's an inherent property of space itself in this model.
Wow, okay. And how does this constant density affect the age of the universe? You mentioned it helps with discrepancies.
Yes. If you only had matter and radiation, the expansion would always be decelerating due to gravity. Calculating back from the current expansion rate would give you a certain age for the universe.
Yeah.
But for a while, that calculated age seemed to be younger than the estimated ages of some very old objects we see, like globular star clusters. That was a problem.
How can the universe be younger than things in it?
Exactly. But adding the cosmological constant, dark energy, changes things. Because it causes accelerated expansion, especially more recently, it means the universe took longer to reach its current size than it would have without dark energy. The expansion was slower in the past than a purely decelerating model would imply.
Ah, so the acceleration stretches out the timeline, allowing for an older universe overall.
Precisely. It resolved that age problem quite nicely. The dimensionless age, HEO, is larger in a lambda CDM universe.
So dark energy doesn't just accelerate things, it helps the cosmic clock make sense. Okay, one last thing you mentioned, key evox. What was matter radiation equality? Why was that important?
Right, matter radiation equality.
Yeah.
That was a specific moment in the early universe, maybe around 50,000 years after the Big Bang. It's a point when the energy density of all matter, ordinary and dark, finally overtook the energy density of radiation.
Okay, so matter became dominant over radiation.
Yes. Before that point, the universe was radiation dominated. The intense bath of photons exerted a lot of pressure, and this radiation pressure effectively prevented small density fluctuations in matter from collapsing under their own gravity. They couldn't really grow.
The radiation smoothed things out?
It resisted clumping, yes. But once matter became dominant, its gravity took over. Those tiny density fluctuations the seeds planted much earlier could finally start to grow seriously, pulling in more matter. That process, gravitational collapse, eventually led to the formation of the first stars, galaxies, and the large-scale structures we see today.
So matter radiation equality basically flipped the switch, allowing structure formation to begin in earnest.
It was a really critical transition point for the universe's entire architecture.
Fascinating stuff. Okay, let's try and wrap this deep dive up. We've covered a lot of ground.
We certainly have.
We started with that shock. The universe isn't just expanding, it's accelerating, driven by, well, something we call dark energy, likely this cosmological constant.
The simplest, yet strangest explanation, perhaps.
Then we looked at the mountain of evidence for dark matter, the invisible scaffolding holding galaxies and clusters together, even if our main model, CDM, has some, quirks on smaller scales.
Quirks that keep theorists busy, definitely.
And we touched on the big picture, the cosmological principle, the FLRW metric, describing expanding space, and how the different ingredients, matter, radiation, dark energy, dictate the universe's evolution via the Friedmann equations.
Yeah, it's really about that interplay between the contents and the expansion, governed by these fundamental principles. Hopefully it's given you a clearer framework for thinking about these profound cosmic questions.
Absolutely. And now maybe a final thought to leave everyone chewing on. Okay, so dark energy and dark matter. Together, they make up something like 95% of everything in the universe. 95%. And we fundamentally don't know what they are. So what truly revolutionary shift in our understanding of physics, maybe even reality itself, might be needed to finally figure out what this dark sector is made of and get a complete picture of the cosmos we inhabit? It just highlights how much we still don't know, doesn't it? And how much more there is potentially out there to discover.